So far in this course, we've spoken a lot about motion, but specifically translational motion, in which an object moves in a straight or a curved line. Now let's turn our attention to the motion of rotation of a rigid body about a fixed axis. A rigid body is a body that can rotate with all its parts locked together and without any change in its shape. A fixed axis means that the rotation occurs about an axis that does not move translationally. Here we see a rigid body of arbitrary shape in rotation about a fixed axis, called the axis of rotation, or the rotation axis. In pure rotation, called angular motion, every point of the body moves in a circle whose center lies on the axis of rotation, and every point moves through the same angle during a particular time interval. In purely translational motion, also called linear motion, every point of the body moves in a straight line, and every point moves through the same linear distance during a particular time interval. We'll examine here the angular equivalents of the linear variables we are already familiar with: position, displacement, velocity, and acceleration.
Let's first look at angular position. How do we describe where on the circle we are? So there's lots of ways to do it. Here's two examples. With my twister game, I could say my spinner is on right foot red. Or with my clock, I could say the big hand is on the 5. Both of those describe where something is in the circle. But the conventional way of doing it is to use geometry. You'll remember that in geometry, arc length is represented by the letter S, and so if we say the circumference is 2 pi r, using our equation for angle in a circle, the arc length divided by the radius, we see here, that gives us 2 pi radians. So we can describe any position on the circle with a radian measure. Here's an example. I have this neat looking pi clock, and it is labeled with radian measure around the circumference of the clock, and it starts with the conventional positive x-axis being 0, and just like in geometry, we measure positive angles through the first quadrant, then the second quadrant, then the third quadrant, then the fourth quadrant. In other words, we measure counterclockwise for angle measurement to be positive. So here we see the clock has been divided up into 12 divisions because there are 12 numbers on the clock. 0 to 90 degrees is 0 to pi over 2. 90 to 180 is pi over 2 to pi. And 180 to 270, pi to 3 pi over 2. And 270 to 360, 3 pi over 2 to 2 pi. And you can see the other numbers on the clock have been replaced by 1/12 increments of 2 pi. So we can use these numbers, these radian measure, to describe where we are on the circle. Also, let's remember, one time around the circle is 360 degrees, or 2 pi radians. From that, we can figure out that 1 radian is 1 over 2 pi revolutions, or 0.159 revolutions, which is 57.3 degrees. And if you keep going around the circle more than once, you just keep adding up the radians. So 2, just like you add up the degrees. So 2 revolutions would be twice around, or 2 times 360, 720 degrees, or 2 times 2 pi radians, 4 pi radians going around the circle twice. Let's look now at angular displacement, or how much did we change in position, moving from one position to another? So we'll do an example here, moving from the 9 o'clock position to the 10 o'clock position. So our final position would be where 10 is on the clock. That's 5 pi over 6 radians. And our initial position is where the 9 is on the clock, pi radians. So that difference is negative pi over 6 radians. So we've changed by a magnitude of pi over 6, and we've moved in the negative direction. A good thing to remember is that clocks are negative. So just like our coordinate system, when we move clockwise, our angle measurements are negative. To go from the positive x-axis to the negative y-axis, that's an angle of negative 90 degrees. And if we go in the counterclockwise direction, that's the positive direction on our coordinate system. From the plus x-axis to the plus y-axis is an angle of plus 90 degrees. So remember, clocks are negative. And just like with linear position as a function of time, we can also use similar equations to describe angular position as a function of time. So for example, at 5 seconds, at t equals 5 seconds, my position will be at 72 radians. And if you want to find out where on the circle that is, you can divide it by 2 pi. That's 11.46 revolutions. So that means you can ignore this 11. That just means it went around the circle 11 times. And now it's located at 0.46 of a revolution, which is a little less than half of a revolution, which is a little less than 180 degrees. So it'll be somewhere in the second quadrant near the negative y-axis. Now let's take a look at angular velocity. To denote angular velocity, we use the Greek letter omega. It looks like a little W. Just like with linear velocity, it is the change in position, or the displacement, divided by the change in time. So we write that theta 2 minus theta 1 for our change in angular position, or our angular displacement, divided by t2 minus t1, or delta t, our change in time. And that will give us the average velocity. And the units of angular velocity are radians per second. Let's look at another example. What is the angular speed of each of the 3 hands of the clock? So we're going to apply our formula, and we're going to take the one time around the circle to be our angular displacement. So that's going to be 2 pi radians. So for the hour hand, we know it takes 12 hours to go around the clock once. So we need to convert this to give us units of radians per second. So just like we learned with unit conversion in chemistry class, 12 hours multiply by 1 hour over 60 minutes and multiply again by 1 minute over 60 seconds. And we see our units of hours cross off, our units of minutes cross off, and we're left with radians per second. Here's our answer for the hour hand. For the minute hand, it goes around the circle 2 pi radians in 60 minutes. So I only have to use one unit conversion to change the minutes to seconds, and I come up with my new answer for the angular velocity for the minute hand. And for the second hand, all we do is divide the 2 pi radians by the 60 seconds to come up with our answer for the angular velocity of the second hand of the clock.
Let's measure the angular speed of this record player.
So it turned 4 times in 5.1 seconds. So I'll divide 4 revolutions by 5.1 seconds, and I want to convert this to revolutions per minute. So I'm going to multiply by 60 seconds per minute to come up with 47 revolutions per minute, or 47 RPMs. The reason I did this conversion here is because this is another common unit of angular velocity, rotations per minute. So radians per second is a common one, and revolutions or rotations per minute is another common unit. And again, in the same way we treat finding linear acceleration from linear velocity, we can find the angular acceleration by taking the change in angular velocity over the change in time for our average acceleration alpha. And the units of acceleration are radians per second squared.
This poster up here on the wall has been there all year, and we haven't really talked about it at all. You may have seen it. You may say, I don't care. But today's the day we're going to introduce it. When you look at those equations, you say to yourself, oh, those look kind of familiar. And you might notice they are those equations over there. Except those are for linear motion. Now we've got a set of equations for angular motion. Okay? So on the other poster, D stands for displacement. On our new poster, D is replaced with delta theta, our change in angular position. So to use this clock as an example, if I were to start at the 9 o'clock position, which says pi radians, and move to the 10 o'clock position, which is 5/6 pi radians, what is my displacement? What is my angular displacement? Well, we always say theta final minus theta initial, so that would be 5 pi over 6 minus pi equals negative pi over 6. So in other words, I have displaced pi over 6 radians and in the negative direction. Remember, for our coordinate system, it's traditional to move in the positive direction from the positive x-axis. The positive direction is in the counterclockwise direction. So through the first quadrant, then the second quadrant, then the third quadrant, and the fourth quadrant. That's the positive direction. So from moving from here to there, I've moved clockwise, so it's negative displacement, and the amount of it is pi over 6. So I've got both my magnitude and direction that tells me which way I moved and how much I moved. Okay. So that's on our poster. Delta theta is our angular displacement. Velocity over there is our linear velocity. On this poster over here, omega, the Greek letter omega. It looks like a W kind of. And that is our angular velocity. And everywhere over here that you see an alpha, that was an A over there for acceleration. So these are our angular equivalents of the linear equations of motion. So delta theta for displacement, omega for angular velocity, and alpha for angular acceleration. Okay, so the similarities, there are a lot of similarities. Even though all the variables have different names, there's still displacement, velocity, and acceleration, just now for angular. And as with the linear equations of motion, the same rule applies for the angular equations that says they are only valid when the acceleration is constant.